welcome to another episode of Lost in Science. This is half an hour of science. Who are we? I'm Kat, and I've got Stu and Chris. How are you both doing?
Great,
well.
thank you. Yeah.
Brilliant. I'm excited for some science. So what science have you brought in for us to mull over? Stu?
Well, I'm actually talking to a psychology expert, Associate Professor Adam Osth from the University of Melbourne. He does research into cognitive and computational psychology, but I'm just going to have a chat with him about some research that caught my eye regarding differences in brains between people of different genders and why maybe that's not quite the particular journal article that I'm talking about is suggesting something which is not actually supported by the data that they're presenting in their paper. So I wanted to get an expert's opinion on this, who's got more of a psych background than me. But yeah. So anyway, I'll be talking to Adam a bit later in the show.
Awesome. And Chris?
Well, it's not only psychology, I guess, that has results that might be a little bit, I don't know, unreliable, perhaps. This is a medical one, though. This is something that I saw a headline in my science newsfeed, and I thought that seemed like quite startling. It sounded like a big story. The story was that tattoos seem to increase your risk of certain types of blood cancers.
Whoa.
I did see this as a news article, but I didn't read too much into it. So I guess you're going to jump in and find out what's going on there.
Yeah, I am going to jump in. Look, yeah, I haven't seen it in the news too much, and there might be a reason for that. Look, it is less dramatic than it sounds at first. Look, it's still an interesting study and some interesting findings, but yeah, look, don't go panicking just yet. And certainly, as we'll find out, don't rush and get your tattoos removed if you have any. But yeah, look, it's an interesting story, and I guess, a bit like your story, Stu, it gives some lessons in how to interpret these kind of studies when you see them reported in the media or wherever you see them reported, and the things to look out for.
Hopefully we'll learn lots, or I'm sure we will. So, on with the show.
Okay, yes, listen to Lost in Science, and I am talking about the question of, could tattoos give you cancer? Yeah, there has been a new study published. Cancer Council in Australia has a few different kind of state bodies, but the overall cancercouncil.org.au had a page that says, does tattoo ink give you cancer? And they basically say that they're not aware of any definite risk, that there are some carcinogens, some known carcinogens or believed carcinogens in tattoo ink, or possible carcinogens, I suppose they should say. But they go on to report that a recent review found the number of skin cancers in tattooed skin was low and seems to be coincidental. Now, the first obstacle I came across with this, though, of course, was this. I just found this page on their website. It didn't have a date on it or anything like that. So when it said a recent review found that the number of skin cancers was very low, I was like, which recent review? There's no link. There's no date. How recent are we talking here? And I even went to the source code of the webpage because I am a IT nerd. And there was no date in the metadata or anything like that. I was a bit frustrated. The Wayback Machine couldn't even reliably help me. But I since have been down plenty of rabbit holes. I'm pretty sure I identified from other references that the paper was one that was published in 2012 on the question of tattoos, inks, and cancer.
So not that recent.
The page is quite old. You could tell by looking at the page it was quite old. Let's just say there. And there was, from their question answer section, called I heard, as in small I heard. So anything, I guess, that had an I usage like that probably is going to be about the 2010s, let's be honest. So yes, a lot could have happened in the decade or more since that was published. But yeah, look, that article though did acknowledge that so with tattoos, people obviously have looked at the question of skin cancer because the inks are injected into the skin and they stay there clearly permanently in the dermis of the skin, but they may be transported to other parts of the body, in particular into the lymphatic system and the lymph nodes. The lymph nodes, the lymphatic system is a kind of other circulatory system we have. Kat, you know all about this. Why am I explaining this to you? And it produces the lymphocytes, the white blood cells that hunt germs. Is that a nice, simple way of describing it?
Yeah, it's a hub.
They did correctly, I think, identify that perhaps the lymphatic system may be, or the lymph nodes may be somewhere to look for this. So, and that has led us to this more recently published study from Sweden, which is on a Lancet journal, but not the Lancet. The Lancet is like one of the top medical journals in the world. This is from their stable of journals. It comes with the URL saying the Lancet proudly, but then you go, oh no, hang on, this is eClinical Medicine. It's not quite the same as being published in the Lancet, but it is a study from Sweden called "Tattoos as a Risk Factor for Malignant Lymphoma: A Population-Based Case Control Study." So what they did here, Crystal Nielsen and her colleagues from Lund University in Sweden, they basically got all the cases between 2007 2017 of people aged between 20 and 60 years who had malignant lymphoma, and essentially tried to follow up to see whether they had tattoos or not. They basically tried to use all the known cases of lymphoma, and then they would then match them to a population control sample to try and get some epidemiological data. Is there a relationship between being tattooed and having these particular type of cancers? They had about a 54% rate of response from people they contacted, basically to ask, have you ever been tattooed? And they about, I think, 21% of those people in their cases of they had 1,398 people who'd actually responded who had the cases of lymphoma. 21% had tattoos, and they had a sample of over 4,000 people who were their controls, and 18% of them had tattoos. And what they found is there was indeed a higher rate of lymphomas in people who had tattoos than people who didn't. And this is what you may have seen reported. If you have seen this in the news, there was a 21% higher rate of malignant lymphoma for people who had tattoos, which is quite startling. The rate was high. The rate was highest in the first couple of years after getting the tattoo, the radio association, and it was also highest for two particular types of lymphoma: diffuse large B-cell lymphoma and follicular lymphoma. Kat, can you explain what these might be? Are you familiar with lymphomas at all?
A little bit, but yeah, it would be the certain type of immune cell that's impacted. And so, with a B cell one, you're impacting particularly the B cells, and your whole immune system is going to be going down, but each of these can impact you in slightly different ways.
Yeah. The diffuse B cell lymphoma is apparently the most common form of non-Hodgkin lymphoma. Follicular lymphoma is the second most common one, and that's one where it affects the follicles that produce the B cells, is my understanding. What was also interesting, though, is that there was no evidence of the more tattoos someone had, the higher their risk of lymphoma. They just observed that, so it just seemed to be the presence of the ink at all that led to this connection. So, look, it sounds quite startling, doesn't it? 21% higher chance of lymphoma with tattoos. However, there's a few things to note with this. The first thing to always look at when you get these reports is, of course, the confidence intervals. Is this result actually what we call statistically significant? So when they report these things, they might give you in the case of relative risk, a 21% higher chance of getting lymphoma. But then they tell you it's a 95% chance of the actual real number, statistical calculation, 95% chance of it being between a range. And if the range crosses the number 1, which is basically it's the same risk, then it's known as basically it's not statistically significant. And in this case, it is really borderline. The 21% risk was from between 0.99 to 1.48. So it's officially not a statistically significant result. So they found this essentially an association that looks like it might be something, but it's not a real result. So scary, but it's not proven, I guess you could say. And they don't know the mechanism, we should point out. They don't know the exact mechanism that might be causing it. They haven't got laboratory results that sort of show, say, in cells in a dish that they could reliably produce this form of cancer. So it doesn't, it's just kind of an association that's there to scare everybody, essentially.
It's one of those, like, you have those things that sound scary, but it's always like, is it correlation or causation?
Yeah, and they tried to get rid of confounds. They tried to control confounds. They admitted that it can be really difficult to do. And certainly in the epidemiological studies, that's always the case. There can often be other confounding things. Yeah, it could just be correlation. Look, the other thing that kind of stood out for me, so there was a figure they got that was statistically significant, and that was this result, this association in the first 2 years. That was a much higher risk, is 81% chance, relative risk, increased risk of being within the first 2 years of having a tattoo and having a lymphoma diagnosis. However, they did acknowledge that there could be reverse causation, because sometimes people get like medical tattoos or little guides for the radiology. They tried to control for that as well and said they couldn't remove the association, but reverse causation is actually a possibility there. The cancer may be causing the tattoo in some cases, but just the very fact that it was highest in those first 2 years, then it actually went down, the association, and then it went up again after about 10 years or so. And whenever you see these results that go up and then down and then up again, I don't know, it's always a bit of a red flag for me, because what is the mechanism here that's causing it to change over time? It just seems a bit suspect and maybe a statistical artifact. If the whole thing is not real, that would explain all of that quite nicely. The also thing to consider when you see these kind of results is, as I said, 21% higher risk, but you also have to consider what is the absolute risk here. So not just the relative risk, might increase the chance of the lymphoma, but also how much what is the actual absolute risk of your likelihood of getting it. Now, this was a bit hard to get a handle on, but the strongest result, they said, was for diffuse large B-cell lymphoma and follicular lymphoma. From the statistics I found, they together seem to have a prevalence of about 10 cases per year per 100,000 people. So and each of them had actually a 30% increase risk from the tattoos. So if you're 30% on top of that 10 cases per 100,000, that is 3 cases per 100,000 people, which isn't huge. It's not great if you're one of those 3 people, but again, it's not a huge number. This is not what we'd call a common condition, that of tattoo-induced lymphoma. And also consider that there were plenty of people who had lymphoma but didn't have tattoos as well. So clearly it's something that happens a lot regardless of people's tattoo status. I'm just going to have a sip of water, excuse me. So yeah, it's not the most, it sounds scary, but not necessarily from the statistics the scariest thing ever. Although, having said all that, I compared it to the kind of rates association for non-Hodgkinson lymphoma that have been reported with glyphosate. And it's basically comparable, what we're seeing with this tattoo study, to the kind of results that have been reported, similar level of statistical significance, similar kind of relative risk. And people are doing all kind of precautionary responses to glyphosate. So, there's a question of whether, someone should consider the same kind of factors with tattoos as well. But the important thing to acknowledge, I guess, is don't get your tattoo removed if you are concerned about this, because they also found that there was an increased risk with tattoo removal. That, in fact, there was a 163% increased rate of lymphoma with people who had laser tattoo removal. Again, not a statistically significant result. In fact, there's quite a large confidence interval here because the numbers are so small. But, yeah, and that could be explained. Like, if you're actually sending a laser to get rid of these chemicals that are in the skin that perhaps could cause them to distribute to the body more. So there is a potential reason for that. So I suppose the takeaway here is, this is like a scary sounding result. More research is needed, though. It's not proven. But if you're the kind of person who's likely to jump to conclusions about this, then you should also jump to the conclusion that don't get the tattoo removed as well, if you already have it there. So, yeah, that's what I got from this.
I think we're lost.
We're not lost.
Not even any short-range radio signals yet?
Except for a single, very powerful radio emission.
Of course, a transmitter of that sort isn't exactly standard equipment.
Science and technology must be absolutely mind-boggling.
Of course, it's mostly on the theoretical side.
Well, so far.
Across Australia on the Community Radio Network, you're listening to Lost in Science.
Now, I've got with me today Dr. Adam Osth, who's Associate Professor of Psychology at the University of Melbourne. Thanks for joining us on Lost in Science, Adam.
Oh, thank you for having me.
The other day, I saw you talking about a study out of Stanford, which was a psychological study, and they're making some claims about some work they've done, which you sort of suggested was not really what they'd demonstrated with their study. So do you want to just give us a brief description of what that study was and what they were saying?
Well, it was an MRI study where it looked as if they had scanned men and women's brains while, I think, performing a series of different cognitive tasks. And what they concluded was that they were able to classify on the basis of brain activity almost perfectly whether people were men or women. And from that, they concluded that they could reject the gender binary. I think that was a major stretch on the basis of what they had actually done.
The use of MRI to look at brain activity, that's been widely used for a number of things for years. Why were they particularly trying to use it to distinguish between male and female brains? Or was that even the purpose of the study?
I think what they were trying to understand was they were trying to understand ways in which men's and women's brains are different. And there's a lot of research on that topic, but I think what they maybe had not done so well is you need to really kind of think a bit more critically on what these differences actually represent. One of the first conclusions people will jump to when they find differences is, therefore that, they might be inclined to conclude that differences between brains are genetic in origin or biological. That's not actually warranted at all. The brain is actually highly responsive to experience. Even on structural MRI scans, somebody who would, for instance, take up learning a stringed instrument or some kind of new musical instrument, different structural differences in the brain can be evident almost immediately, within days or weeks of experience. And when I say the changes are evident, I mean they're measurable on structural MRI, which means that there might even be there are likely changes in the brain happening almost instantly that we just can't record. So we know that the brain's highly responsive to experience. So for that reason, concluding that any brain differences you see may be for other reasons having to do with gender. For instance, we know that men and women behave differently, they act differently, they're subjected to different experiences in their environment. We cannot rule out that those are responsible for brain differences. So the gender continuum refers to this idea that is very popular right now, that genders are not strict binaries, but that there's a range of different kind of behaviors or cognitive abilities that, vary continuously between the genders. In other words, that another way of thinking about this is that maybe men and women are a lot more similar to each other than we think, in the same sense that, we could look at a lot of different natural categories, have a lot of things in common. For instance, any two brand of cars, like for instance, Corvettes and Ferraris are actually a lot more similar to each other than the between category differences, if I'm making any sense here.
Yeah, so I think so. You're sort of saying that if you were trying to distinguish between Fords and Ferraris, you would ignore a whole lot of things that they have in common, and focus on the differences so that
Exactly.
you would get better results, because you'd say this is a Ford and this is a Ferrari, because you're ignoring those. Oh, they all have 4 wheels. Well, that's not going to help
Yeah.
you make the distinction. So you sort of, if you're designing a program, or you're using machine learning to try and pick differences between things, you're going to ignore those differences, or ignore the similarities rather that they have, because that's not going to help you get your machine working better.
Yeah, that's what I was just about to get to, which is that they based this rejection of the gender continuum in their study on the basis of a technique they used in machine learning, which is very popular in neuroscience. So in neuroscience currently, a lot of times people will subject their data to a machine learning classifier. And what this basically does is it takes all of the data in their study. So in their case, what they have is recordings from, all over the brain. It's massive, massive amounts of data, way harder than to analyze or understand than most people really appreciate. Even trained scientists have a difficulty with that. And what they do is they kind of try to subject this to a classifier that could kind of essentially take aspects of the data and learn to predict something about this data. In their case, whether or not on the basis of brain data, were they men or women. And what it does is it learns across many iterations, and the way it basically operates is by kind of increasing the weight for certain things that are predictive and decreasing the weights for things that are different. Or sorry, decreasing the weights for things that are similar and increasing the weights for the things that are really distinguish between them, to kind of hone in on whatever's diagnostic and different about them. And what they found was they were able to, after doing this, predict gender with 100% accuracy. And for that reason, they concluded that the gender binary was wrong. This is problematic for many reasons. One is that a notorious thing about these classifiers is that they can almost always or get very, very high accuracy. This is a problem referred to as overfitting models, in that they can usually train very well on the data set they were trained on. But as soon as you try to generalize them to novel data sets, accuracy drops. And so that is, of course, actually what they did end up finding in this result, was when they when they subjected their classifier to a novel data set, accuracy dropped to about 80%, which is fairly normal with these kinds of things. Whenever you predict data that you're trained on, you can do very well.
Yeah, if you've seen the quiz answers, you're going to do all right in the quiz.
Yeah, it's kind of the basic idea. And 80% is still impressive, but I would still argue that, there's a deeper problem with this in rejecting their claims of rejecting the gender binary, which is that, the classifier itself was taught to ignore the similarities between them. That's what they do. So getting high accuracy on classification doesn't necessarily tell you that there's no gender binary.
Yeah, it kind of seems like they've jumped from what they did find, which may well be very interesting data and really interesting findings, but then they jump to something which is not the experiment doesn't seem it was designed to come up with that answer. They've just pulled that answer out of it and said, "Here's what we found." It just seems a bit of a sidestep.
No, exactly, and this is something that a lot of neuroscience, I think, is starting to kind of come to grips with a bit, which is classification methods are used very widely, for instance, for all kinds of things. It might not necessarily be about subject differences. It could be, for instance, predicting whether or not people remember or forget things on the basis of brain data. So you could, for instance, subject people's brains while they're seeing something new to a classifier. You could then kind of learn to make predictions about the things they remember or forget and find brain differences on these bases, but they're very difficult to interpret. And learning that you can classify these things may not always give the knowledge that people think they're getting.
This seems like it's sort of a crossover between neuroscience and psychology. Is that always going to be a bit of a multidisciplinary thing? They're not exactly the same thing, are they?
No, they're not. And yeah, that's something that is also frequently being argued about, is what the brain can tell us about psychology. I think it can tell you a lot, but it does require some pretty careful skepticism to really understand what kinds of psychological questions you can answer by studying the brain.
Looking at the mechanics of the way the brain works is not necessarily going to give you a psychological view of the person whose brain it is that you're looking at.
Yeah, I would agree with that. It can in some cases, but it requires a lot of really careful understanding and interpretation of the neural data.
And so you use neuroscience in your research. What sort of things are you working on with that in that area of memory, which I know is your main field of focus?
So I have just gotten into this recently. I haven't done a lot of neuroscience work, but typically the kind of work I've gotten into is looking at EEG signals. So EEG is a way of measuring the electrical activity in the brain. So typically people wear a set of electrodes over the scalp, and we can measure people's electrical activity while they are doing various things. It's very popular in sleep research. So a lot of what we know about sleep brain waves comes from EEG recording. But it's also used in memory work a lot, which is my area. So I study human memory primarily. And one of the things we can do is we can measure people's brain activity while they're basically performing some kind of memory experiment. What I've been doing with a PhD student of mine, whose name is Jia Sun, he has been looking at the kinds of brain signals that signal various types of remembering. And what we're doing is exactly actually what I was saying before, is we're actually trying to adopt a more skeptical view of the types of brain signals people have uncovered previously. So for instance, people have made claims that there are brain signals that are different depending on the type of remembering that people perform. So some people, for instance, believe that there is a kind of familiarity-based memory as well as a recollection-based memory, and that you can find different kind of regions in the brain and different timings as well that are responsive to that. I'm actually a bit more skeptical about this view and believe that we can actually these might just be different signals, different brain responses to the same underlying signal. And that's the kind of research we've been performing recently. We've been able to find that, certain aspects that have been previously interpreted as a kind of, direct retrieval of event details actually might even just be something as simple as signaling when people are actually ready to give their memory response. In other words, that there's just some simple kind of uninteresting explanation for what people have been previously arguing about and thinking is actually a big deal, which doesn't necessarily sound like a very sexy result, but that's kind of our point, which is that you need a lot of skepticism and care in interpreting these neural results.
I mean, yeah, I think in general across all of science, the boring explanation is never quite as much fun and harder to write a paper about in the end.
Yeah, but unfortunately, the boring explanation is usually the right one. 9 out of 10 times. So
yeah. Well, I think we should probably wrap it up there. That was really interesting, and I'd love to get you back and talk about some more of your research, and maybe even get some of your PhD students on to talk about their research, which would be hopefully good for them and good for us as well to hear about what's going on. But yeah, thank you for joining us on Lost in Science.
Thanks so much for having me.
And that is all we have time for this week on Lost in Science. Thank you for joining us in Getting Lost. If you have any questions or suggestions for the team, get in touch with us by email. We are lostinsci@gmail.com. You can send cheap tweets to us at lostinscience1 on Twitter, or you can find us on the ubiquitous Facebook. Lost in Science is recorded at the studios of 3CR in Melbourne on the land of the Kulin Nation and is broadcast across Australia on the Community Radio Network with the assistance of the Community Broadcasting Foundation. You can find a podcast version of the show on 3cr.org.au, or you can tune in the way you did this week when we return in our usual time slot to get lost in science!
Thanks for listening to a 3CR podcast. 3CR is an independent community radio station based in Melbourne, Australia. We need your financial support to keep going. Go to www.3cr.org.au for more information and to donate online.